In this video, we're going to look at linear models and estimation by least squares. So when we take a look at linear models, we might be looking for an equation that relates two or more variables. Right? So typically we think of a response variable, a dependent variable y, and an independent variable, a predictor variable x, or possibly multiple predictor variables. We'll look at just the case where we have a single predictor variable, and we're going to look specifically at trying to obtain a model y equals beta 0 plus beta 1x. Right? So when we're trying to find this model, what we're trying to do is we're trying to identify what is a value of beta 0 and what is a value of beta 1 that would make sense, that is kind of best in some fashion, that best models this situation. Now, I say best models the situation because in reality, when we have that, what we're really saying is we're trying to find this model where the expected value of our y is equal to beta naught x plus beta naught plus beta 1x. In reality, we have some kind of error, some kind of small change that might happen out here. And so when we think about what this looks like, we might think it looks like this, beta 0 plus beta 1x plus some epsilon. We should think of this epsilon as being some small error, but that epsilon is this small error with this specific property that's a random variable possessing a probability distribution with mean 0. So on average, this value is 0, and so if we're just trying to guess a value for our function, then, or guess a value for y, then this equation up here makes sense. We would guess that this is 0 because on average, the mean is 0. So sometimes people want to know what is this, the one best guess, and other times people want to know what is like a range of guesses that would make sense based upon what this assumed distribution for the error is. So that's what we're going to be looking at. We'll be looking for these models. This first model up here, we call that a deterministic model because it does not allow for any error in predicting y as a function of x. Or rather, sorry, my bad. Our deterministic model is right here. And then down here, so that's our deterministic model. Further down, we see our probabilistic model because it allows for those errors to occur. Beautiful. That first one was a deterministic model. That value of y, it is going to take on a specific value when we know the value of x, because we plug in the value of x and it will spit out a specific value of y. It is completely determined by that value of x, provided we've already identified a beta naught and beta 1. So how do we find the beta naught and beta 1? And so if we're looking for that beta naught and beta 1, one method we might use is the method of least squares. So we'll look at that. This is trying to find a linear statistical model. It is linear because the power of the predictor variables are all power 1. We will be looking at specifically stopping here for our linear statistical model. And the expected value of our model will be this. So we're going to say the expected value for that error is 0. So the method of least squares, this is the method. we observe a bunch of pairs of data. So say we observe n pairs of data. We're trying to model the expected value of y as this linear function. And so the estimated values of y associated with each of these x sub I are shown by something like this. So we use a hat to identify an estimated value, not an actual value. And right now we should imagine these B naughts, the B naught and B1. Those are unknown and to be determined. We don't know the best values yet, but through this process we're going to identify the best values. All right, so the best choice of beta naught and beta 1 hat is the one that minimizes the sum of the squared differences between the observed, the actual y sub I, and the y sub I that we would get using an estimation like this up here. And so we're looking at this, and we're trying to minimize that. So this sum, SSE, that is the sum of the squared errors. It is also called like sum of the squared residuals. And we want to minimize this. If we are looking to minimize this, then it is going to satisfy the partial derivative of that with respect to beta naught should be 0. It should also satisfy the partial derivative of that with respect to beta 1 hat. It should also be 0. And when we do that, we get a specific formula. And we will talk about that specific formula for beta 0 and beta 1 in the next video, along with an example where we go through this. All right, I will see you there.